Okay, great. So we're really pleased to have Xinwen Zhu from Stanford, who will tell us about the tame categorical local language correspondence.
Great, thanks for the invitation. Really pleasure to come to this program. A couple of days, a lot of fun, so many people. All right, so this is about tame categorical local language. I gave various versions of this talk in the past couple of years. Hopefully the article will really finally come out soon. But in the meantime, there's some new development. There's at least something new. Right, so let's start. So let's first record the classical local Langlands, which is the statement is the input data is a non-committing local field F, and the reductive group over F. So it's basically have some pick some notations. The gamma F is a Galois group of F, and the WF is a wave group. And you can form the usual Langlands Q group. This is some final extension of F, such that the action of Galois group on the Q group on the root data factors with this finite quotient. The classical local Langlands correspondence, roughly speaking, predicts a bijection between smoothly reducible representation of this p-adic group GF and the homomorphisms from the wave group to the L group up to G hat conjugation. This data is called the Langlands parameters, subject to some conditions on this homomorphism, which I will not mention. It's not that important for this here. For GON neutrality, of course, this is just two sets of kind of infinite cardinals. To make a bijection, you want to satisfy a bunch of conditions. So this is natural bijection. The neutrality can be made precise. When GON, it's kind of easy to make the neutrality precise using epsilon factors and L functions. It's really a theorem in local Langlands correspondence. When characteristic is positive, this is proved by Lamont, Rappaport, and Stuhler in 1990s, and when characteristic zero is proved by Hurst-Taylor and independent by Henya around 2000. For general group G, the natural bijection, this neutrality is really hard to formulate. I know people are working on this and put various conditions on natural to make this precise. Because if you want to prove some bijection, you better have a precise definition what to prove. But anyway, this is hard. So in fact, even the set of Langlands parameter needs to be enhanced. It's not just the parameter. I think the earliest, I didn't really look into the history, but probably the earliest results in this enhanced parameter is this Kashan-Lustig's classification proof of the Langlands conjecture, which classifies smoothly reducible representation with your horifix vectors. Though there, then you see such representation. This is just a small fraction of all smooth representations. But if you want to get the parameterization, what do you need to attach to such a representation? It's not just the Langlands parameter, but also a representation of the centralizer of this parameter of the conjugation. So, and of course, what appears here is not the arbitrary homomorphism, but those factors through the tame in which is those Langlands parameters that are trivial on the wild inertia. And here is not all the representation of the centralizer appears here, but it appeared only some of them appear like programming some like the homology of some certain fixed point of Springer fiber, which I don't want to go into details about that. But anyway, the point is the whole punchline is the appearance of this rho actually suggests that there are stacks involved in this story. Namely, what one should really think about rho is it's a representation of this group. Let's say it's a reductive group, but you should really think about it as a vector bundle on this quotient stack point modulo this group. and which then you can also think about this quotient is the g-orbit of this homomorphism phi modulo g hat. So therefore, actually, then of course there's a between Kachelin-Lustig and nowadays there's like almost 40 years, and there's a lot of developments. But anyway, particular development is this geometric Langlands, which suggests actually even the classical Langlands probably should be lifted into a categorical level, which also fits this should also be understood in like some quantum field theories in this program is about sort of okay. So indeed, there's a such thing. So because this is bijection, Langlands is bijection of two sets. So both sides should involve some stacks. And so let's start from the easy side, which is spectral side, which is some more familiar traditional objects. This was the following thing. So there's actually an algebraic stack over ZL. Let's fix, we'll do L not equal to P, it's a local Langlands. Then there's a algebraic stack classifying continuous homomorphism from the wave group to, I used to use C of G, the C group, it's like the variant of the L of G. You can, I mean, if you are willing to adjoin the square root of Q here, you're free to replace LG, CG by LG. Okay. Anyway, so there's such space, algebraic space, which is parameterized continuous homomorphisms from the wave group to C group, and this space is represented by disjoint union of reduced finite type affine schemes, which are each one is even local complete intersection flat of relative dimension G hat over ZL. So this is really just, well, it's I mean, if you don't talk about the topology, this is quite classical. It's just considered the representation space from home, let's say, a discrete group to GON. If the group, let's say, is finite generated, you just need to specify where the generator goes, and the relation, where the relation goes is clearly represented by a closed subset in several product of your group. But of course, here you need to sort of deal with the continuity. One needs to a little bit careful, but it's not really difficult. Just to figure out the correct continuity. This really means for every R, consider any vector here. You consider this subspace, sub-ZL module generated by V under the action of the tame inertia. You want this is a finite ZL module, and the action of inertia is continuous for the usual L-adic topology. The problem in general is when R is not a finite ZL module, just there's no good topology on R. So question? Can
you say something for L-equal speed?
Alex, I won't. The whole story is about L not. Okay. Anyway, this is about quite. Then the stack of representation is just this one modular quotient of G hat. So it's some really classical objects, and then what the spectral side or Galois side, what we should consider is categorical coherent shifts on this stack, which really means just the modules or maybe coherent shift on this affine scheme equivalent to a G hat equivalent coherent shift on the affine scheme. So it's very classical objects. But then let's move to the representation theoretic side. What I'm gonna describe is what I would like to call local Langlands category. There's some other terminology, but anyway. So if you want to go to categorical, natural thing you want to do is to replace a set of smooth representations of GF by the derived category of smooth representation of GF. But somehow this is not quite enough. Even from the classical point of view, like from Bogan, Hodowitz, Klesha, they said in fact it's better if we want to have a good parameterization. It's better not to just consider the representation of group itself, but always together with so-called pure inner form, extended pure inner form. There's various generality you can consider. But arithmetic geometry, in particular, starting from this Hodowitz work on multi-points of Shimura varieties, actually suggests to people not to just when to study local Langlands, it's better not just study. It's better actually, or at least one version is to study the representation of G together with this collection of group JBF, where this JBF is let me just see. B is kind of it actually has a natural poset structure, which I'm gonna talk in a minute. And each JB is actually a sort of some kind of inner form of a levy of G. Let's say G quasi split. It's an inner form of levy of G, and this is so JBF is also a p-adic group. So it turns out it's better to actually study the collection of such p-adic groups together, and if also all this category representation of different p-adic groups can be glued together as a category of sheaves on some geometrical object when considered. There are two approaches to make this idea precise. One is Frank Schultz is doing this, but like some kind of sheaves on bound G. This is sort of very difficult approach because it relies on deep p-adic geometry on this, some kind of very non-traditional. These are basically analytical objects, basically. So you need to deal with p-adic geometry in analytic geometry, and the definition of this category is really difficult. And there's another more traditional approach in stating completely algebraic geometric world. I think was developed like originally. I think in my work with Liang Xiao on some kind of multi-correspondence between different Shimura varieties. This somehow some version of this appears, and also Dennis has some like also kept this idea how to define such category around the same time. With him, we actually you will see we actually write on like study this category in details. So and then the categorical local Langlands, roughly speaking, take the form you should have equivalence categories between coherent sheaves on the stack local parameters and some kind of constructible sheaves, some kind of construct on this category on this space I saw, which this is something I'm focused on later. So I'll talk more about it in a minute. And of course, the Park Shelton then also conjecture this category is equivalent to this one. So then one would expect even without the local Langlands, these two should be equivalent. And actually, I think very recently, at least when F is a p-adic field, people should be able to prove it. They are indeed equivalent, but their equivalency is a non-trivial way. So it's not right. So okay, right. So then that's good because then there's only one conjecture, not two. Okay. Right. So I'll give as I said, really consider this collection comes from this origin comes from this work of Hodowitz or points of Shimura varieties. But I'm gonna try to, as an audience here, I'm trying to give another kind of motivation, which is.
So does the condensed mathematics just appear on this side of the correspondence with Mark Schultz, or does it appear on this side and on this side?
spectral side, I mean, like this definition doesn't use condensed mass at all, but you can also rephrase it in terms of.
So you don't need it.
You can, yeah, but you don't need it's because in this case it's rather simple.
And then on the other side.
It seems to be the most.
Seems to be necessary.
I don't know, but it seems when you deal with the rational coefficient, it seems to be more. In this approach, it seems to be. I mean, for torsion coefficient, it doesn't. You don't really need condensed mass. For rational coefficient, it seems. Yeah, but this doesn't require any condensed mass. No condensed mass. But I'm giving you another motivation, which is more inspired, more related to geometrical representation theory, representation theory side. So therefore, different sort of things lead to the same object. So this comes from the so-called linguistic theory. So if G is a reductive group of a finite field, the linguistic theory is sort of the constructed representation of G of kappa. Kappa is this finite field through the cohomology of certain varieties. So of course, the linguistic didn't write in this way, but nowadays you can really rephrase their construction in the following two steps. The first is we realize the category of this representation of this finite group, G kappa, is the same as the category of sheaves on the classifying stacks of G kappa. G kappa is finite group, so this quotient is a nice, let's say, Artin stack or the Nemonfer stack. And then the category, let's say, a tau sheaves on it is the same as category of representations. The second is this classifying stack actually is the isomorphic to G modulo the Frobenius conjugation by G. So here sigma is really because it's a variety over finite field, so it has admits a Frobenius endomorphism. This quotient G modulo Frobenius conjugate by G is just point modulo this finite group. This is the people usually call, I don't know, Katz theorem or Langlands theorem. I'm not sure, but anyway, this is in the case of GSGO, it's just a vector bundle on it's a spec R and characteristic P equipped with a Frobenius automorphism is the same as a tau sheaf on spec, a tau local system on spec R, which was original Katz theorem. But what's the advantage of this isomorphism is then this space has more geometry. This is just a little bit too simple, just point modulo finite group. There's not much geometry going on. But when you write it as a G modulo Frobenius conjugation by G, then you can start to play some game with geometry. Namely, you can consider G modulo Frobenius conjugation by B, which is Borel. Consider such map. Then if you could produce some sheaves on here by push forward. You produce sheaves on here, which is the way you construct representations. For example, for each element W in the finite while group, you have G has a Brohat cell, Schubert cell, which is BWB, which then is stable under the Frobenius conjugation action B. Therefore, you can just take the constant shift here on this thing and then push forward. Then what you end up with is actually this representation of the G kappa on the cohomology of XW, which is the linguistic variety. Okay, so this is okay. Is it okay so far? It's kind of So now let me move to the real content. So for that, I need to introduce a few notations. So I'll take OF to ring of integers. KF is resident field with Q element. Sigma is Frobenius, Q Frobenius. And if you are dealing with equal mixed characteristic, we work with perfect algebras, FP algebras. But when you work with equal characteristic, you can take R to be any KF algebra. So we define the disk in the equal characteristic. It's a spec of R double bracket var pi, and puncture disk is a spec of R double parenthesis var pi. So it's a formal disk and punctured formal disk. In the case of mixed characteristic, what you use the replacement of disk would be the spec of WR, the ring of weight vectors. This is an invert P. Okay. Anyway, I think it's already good enough to stick to the equal characteristic case if you're not comfortable with perfect algebraic geometry. So when, in particular, when R is the field K, this is Laurent, just a Laurent field over that field, and we just denote this, and this is also a field. Just denote this field by L. Okay, this is just notation. The Q-Frobenius endomorphism of R induces endomorphisms on this puncture disk. Okay. I still denote by sigma R. It's just a notation. All right. Then we have the loop group of G is that we define the algebra geometrical object in K of F. We define it by function points. Its R points is just the G, the sections of G over a punctured disk. For example, if R is just this residual field KF, its value LG of KF is just a GF, the p-adic group. Then if you inspired by the Lewis theory, then you would expect that to study the representation of p-adic groups, you should study shifts on this quotient of LG modulo Frobenius conjugation by LG, which is what I denote by I sub G. And then this should be closely related to the representation of GF. And one might even hope one can take LG modulo Frobenius conjugation by Iwahori, which is F analog of Borel, and take such map, and then you have some shift here, push forward to produce shifts here. That's somehow the way you should be able to produce representations of GF, the p-adic group. In fact, this is the case modulo the technical difficulties and large chunk of things to really make this precise. For example, even the definition of this quotient, one really need to be careful because now you're taking the infinite dimensional in-group modulus, infinite dimensional in-group. What kind of quotient are you taking? There's actually really two different things. One is take a tau shiftification, one is take H shiftification. They are really different. So anyway, even modulo all these technical difficulties which we're not gonna deal with, there's still a big difference between this affine quotient LG modulo Frobenius conjugation by LG and the G modulo Frobenius conjugation by G. Namely, what happens is this in this loop case, the quotient in the finite dimensional case, when it's a G modulo Frobenius conjugation by G, we said it's just a classifying stack of finite group. So literally, the geometric points consist of only one point. In other words, Frobenius conjugation acts transitively on G. But this is not the case in the loop case. The quotient actually can be interpreted if we have K. We call this L is a Laurent series field over K in equal characteristic, something slightly different in mixed characteristics. And this quotient is by definition is G of L modulo the equivalence relation, and the equivalence relation is given by G and H inverse G sigma H are equivalent for GH GL. You can also interpret it as a G torsor on this puncture disk equipped with what isomorphism of E and its Frobenius pullback. I mean, if once you trivialize the G torsor, you produce an element this isomorphism gives you an element G in GL, and the different choice of trivialization allows you to conjugate your G by this element. So but it turns out this groupoid, this is really groupoid, is independent of K. And the underlying set is usually called the Cotway set, BG. It's unless the group is trivial, it's actually an infinite set. It's not a one-point set. It's an infinite pole set. There's a natural partial order on it. And minimal elements are called basic elements. And these are partial it's a co-set with minimal length, minimal elements, but no largest element, maximum element. And for each element in GL, you can consider the automorphism of this groupoid, automorphism group of this groupoid. This is the JBF I mentioned before. It's elements in GL, such as H inverse B, sigma H is B. So it's really the stabilized automorphism of this groupoid. Yeah, that's it. For example, when B is 1, G is 1, then what you really recover is JBF is GF. So this is the something when B is 1, it's like this G kappa in the finite dimensional case. But in general, JBF is just a set of F points of some inner form of a Levy subgroup of G. Let's say G is quite a split. Okay, so it's still itself is a p-adic group, which is a locally profinite set. And we can regard a locally profinite set as an in-scheme. It's a union of a profinite set. Profinite set is the inverse limit of finite sets. So finite sets are affine schemes. So profinite sets are also affine schemes and in affines. Okay, so give an example. When G is a GN, such data E psi is the same as what people used before. It's called the F isocrystal rank N. So it's basically n-dimensional L vector space equipped with a Frobenius semi-linear bijection. That's because the G totals on the puncture disk is the same as an n-dimensional vector space over. And for example, a typical example is for every rational number can attach such objects. So you have an R-dimensional vector space equipped with such an endomorphism, semi-linear endomorphism. And it turns out that this category of F isocrystal is semi-simple with irreducible objects exactly given labeled by parameterized by rational numbers. The endomorphism of each object is a division central division algebra over F with their invariant lambda. So in particular, JB in this case will be just a group of invertible elements in this division algebra, or maybe the product of several, if the object is a direct sum of simple objects. Okay, and one can, I said that this set has a path order. In this case, you can identify the set as Newton polygons with ending starting from 0, 0. Ending point is x coordinate is n, but the y coordinate would be arbitrary. And one is less than or equal to another if the Newton polygon associated B1 is above Newton polygon associated. Basically, then you see, because Newton polygons are convex, so the minimal elements will be strict polygons. So strict polygons. And they are also parameterized by, these are, for example, GO2, if you take, if you take this 1/2, so this is a two-dimensional space, you get a quaternion algebra. JB is quaternion algebra. If you take the direct sum two one-dimensional simple objects, the JB is a torus, just F cross square. Okay, so this is like the inner form of GO2, and this is like a Levy of GO2. All right, so So now let's talk about the geometry of this quotient. Let's ignore the definition of which kind of quotient you are taking. So first of all, here I can define certain subgroupoid. Find I sub g less than or equal to b. Its R point are just the points here, such as point-wise, the corresponding bx. For each point, let's say even geometric point, this bx. When you restrict to that point, you will get an element in BG. That's a Courtois set, and that is independent of choice your field. And then you can ask whether this bx, because on the Courtois set there's partial order, so I require this bx is less than or equal to b. Okay, let's define the isoc g less than or equal to b, and I define isoc g to be isoc less than or equal to isoc g less than or equal to b minus all the locus where isoc less than b. So a priori, this definition is really bad. You define some algebra geometrical object just by putting point-wise conditions. Usually this is not good, but it turns out it's quite nice. First of all, if you just take one strata, as a B, it's actually pointed, it's only one point, because we said this is independent choice of field, actually. There's only one geometric point, and then this isoc is the classifying stack of this JPF. But if you take this quotient to be the quotient by étale quotient, then you end up with some pro-étale tensor over this group. If you take H simplification, you take a V-bound tensors on JPF under V topology. This map, Ji less than or equal to B, this map is actually a finite presented closing embedding. It means that if I have any map, spec R map to it, then the locus on spec R such that the Bx is less than or equal to B is actually closed subset on spec R. And this closed subset can be defined by Feynman equations. And the JB, this map from isoc GB to isoc G less than or equal to B, this map is an affine open embedding. And quasi-compact. In particular, because of this, so when B is basic, actually, this strata itself is closed because there's nothing smaller than it. So this is closed strata, and this strata is basically G point modulo some p-adic group JB, which is in this case so-called extended inner form of G. All right. So then we talk. This is some wild algebra geometrical objects, not in traditional, not studied in traditional algebraic geometry, but still it has some nice geometrical property. It's just another algebraic stack as we. Then you can talk about shift, because we are going to talk about shifts on it. So let's take a little bit talk about the shift. The shift theory we're going to use is purely in algebraic geometry, so-called the inconstructible, should go co-shift. But it's sort of something familiar with in geometric representation community, but really there are some more subtleties as I should do. So I'll take the coefficient to be either ZL, FL, or QL. So there's any kind of coefficient is okay. And we'll take my geometrical objects are just fix a field with the algebraic closed field. Then for each S of finite type, there's usual constructive sheaf, perfect constructive sheaf on S. It's originally defined, I guess, by the name to study way 2. So it's basically constructive sheaf, but the fibers are perfect lambda modules. And then you take the shift theory to be the incompletion of this. If S is a usual, because we are dealing this infinite dimensional thing, we have to go beyond the finite dimensional situation. If S is in general quasi-compact, quasi-separated scheme, you can always, by Noetherian approximation, you can always write an inverse limit of finite type objects, Si. For each Si, I have the definition, and then I define shifts on S as just the first of all, I define the sort of constructible shift on S as a co-limit of constructive shifts on Si by pullback. And then take the shifts on Si, then take the incompletion of this category. So when lambda is finite, by the way, here it's convenient to actually take the shrink pullback instead. That's the reason what's called the co-shift. In fact, it's basically you take the usual start pullback and take the dual category. That's what happens. So in particular, when lambda is finite coefficient, this is really just the usual constructible shift on S. Then for every scaling pre-stack, it's basically just a functor from the category commutative algebras to category groupoids. Let's see. Then you have a definition of shifts on it by taking the limit of shifts on all S. And this limit is taking the index category from all maps from S to X. So this is a huge object. I mean, there's a definition, but it's really not computable in general. But for any natural transformation, and of course, this transition maps is still given by Schrick pullback. For any natural transformation, you have the pullback functor. It's built into this theory, but for many morphisms, large class morphism, or in particular finite representable morphism, you have a star push forward satisfying all the space change. But in fact, to deal with this situation, you need much more general class. You need to allow to push forward along some much more general class morphisms.
Sorry, what's perfect?
It's just the category perfect K algebras, or just usual commutative algebras. Right. Okay, so let's talk about this. This construction was in sort of, it's not a new construction, but there's some exact features which probably was something new. So first of all, if F is finite type and the lambda is finite, as I said, this category is just the usual category of étale shifts on S. If S is a profinite set, this is more interesting. Then you can, as I said, you can regard the profinite set as the affine scheme. But in fact, you can regard it as the affine scheme over spec Z. Then you can space change to lambda. And what happens is these shifts on SK with lambda coefficient is the same as quasi-coherent shifts on S lambda, because all of them are obtained by pullback from the finite type objects. The most interesting is if S is spectrum of a function field of a curve. Let's look at what it is. Then it's by definition, so it's an incompletion of the constructible category. And by definition, constructible categories are obtained from the constructive shift on finite type objects. S itself is not finite type. So what happens is then you can approximate, write the S as an intersection for all open subsets of K. X, and you are considering constructive shifts on the open subsets of K. So by shrinking this open subset, you get the local systems, because constructive shift always become a local system on open subset. So therefore, what do you end up with if you think about carefully is this category, this constructible categories of continuous representations of this field, unramified almost everywhere. This is different from the usual constructible category of lambda coefficient. It's all continuous representations. So you get So this looks nice because in practice, only Galois representation unramified almost everywhere is what we really want.
Does it come from the Schrick pullback in resolutions?
First pullback is the same as star pullback at the moment. Because I'm taking this, I write the U as intersection of an open subset of K. So it doesn't really matter. Yeah. Okay, so this looks good, but there's also some issue. It doesn't look. Anyway, so first of all, if lambda is finite, this doesn't depend on the base field K, but in general, actually, it depends on the base field. Right, because if, for example, if I take my base field, which just this field, this category really changes. The real problem is actually the pro et al. Descent fields. You can just look at this example and consider what the case of K bar over Kx. You will find it doesn't satisfy descent. Really doesn't. But remember, we are trying to deal with p-adic groups and profinite groups. We do need pro et al. Descent. So this is actually you can see it's kind of bug, but somehow it's okay, not a really big bug here. It turns out what happens is, okay, I'll talk about that later, but I mean, there's some issue when you really need to be careful, but it can be resolved. So now we base change everything to K bar, to K. Now, as I said, now we have this shifts and all this I sub G and I sub GB for each one. And I also actually have the functors between them. I always have Schrick pullback, but then I told you there's some geometry, like the push forward, the IB and the JB are finite presented open and closed map. So actually the star push forwards can be defined. And what's really even better, actually, you can define not just the star push forward, you can even define star pullback, and you can not just define the Schrick push pullback, you can also define Schrick push forward. So therefore, okay, so anyway, there's a statement. The first one is on each strata, the category shifts on it is still like the representation of this p-adic group. So remember, this I identify this as a classifying stack of this p-adic group under pro et al. Topology. So as I said, the pro et al. is some fields, so this is not automatic, but somehow there's some. It really relies on the fact that this group with non-coefficient has a higher measure. So it's not if you replace lambda by FP coefficient, for example, I think it will fill. Then you have all this bunch of adjoint functor, just as usually, if you think about space, the open subspace and the closed complement subspace, then you have the usual shift theory. You have a bunch of push forward, pull back, and a junction. Although these are like a wild world, you still have this, and it behaves just as usual. This induces a kind of semi-orthogonal decomposition of this category. That's just a category of this, which is just a representation of p-adic groups. So in other words, you really glued all this category of representation of p-adic groups for different JB to a single category. Right. So then,
So will you say what canonical means? First one.
I mean, it's just still obtained by descent, but just need to show this in this case descent holds. It's not true in general, but it still holds in this case. The category is compact generated. Compact objects are those only vanish on finite many non-zero on finite many B's, and its restriction to each strata is compact. So this really follows from you have a bunch of adjoint functors downstairs. In the previous slide, Then there's also some self-duality, this category self-dual, namely there's some duality functors and compact objects to its opposite category. It behaves like the usual vertical duality on the usual space. For example, interchange the star push forward and the shrink push forward, star pull back and the shrink pull back. And when you restrict to each strata, it's the so-called cohomological duality or Birchland-Zelinsky duality of p-adic groups. Up to some homological shifts, there are some shifts reflecting that there's some each strata really has some dimension there. Then there's a natural T structure on this, you can glue or different T structure on each strata. Get some T structure. All right. Yes. So then it's natural to make this conjecture. So for simplicity, I'll take coefficient to be QL bar. Otherwise, you need to slightly modify. Assume G is quasi-split with the pinning for real torus, and the E is element in the algebra of B satisfying. In the algebra of the uniform radicals of B satisfying certain condition. And let's fix the additive character. Then there is the conjecture is there is a canonical equivalence between category of coherent shifts on this stack of L parameters and the category I just defined. It should be compatible with parabolic induction intertwining the duality. Here I said there's a duality. On the left-hand side, there's the usual growth and elixir duality, maybe some up to some, maybe corrected by some Gardner evolution or something like that. Then there should be, this equivalence should be compatible with that. It also should send the structure shift to the some kind of Whittaker object here, which is going to be a representation really GF, recall it's JB for B equals 1. So it's representing the GF is shifts supported on the closed strata. So if you have a representation, you can think about the shift on it. Okay, so I guess here I really regard E as a map from the uniform radical B to GA. That's what I. All right, so if lambda is not the QL bar, you need to modify one side of the category. Usually, for example, put some nilpotent singular support condition on the left, or replace the compact object by so-called constructible object, which I didn't define. But actually, on this space, you can also define some constructible shift. It's quite involved. Of course, as I said, there's another version of categorical local Langlands, which here is replaced by Parks-Schultz category. And sort of fortunate now they're really just the same become. So this conjecture, it holds, but it means there's particularly implied the category vector bundles or perfect complex on the stack of low L parameters should act on the right side because it acts on coherent shift by tensori should act on the right hand side. This is usually called the spectral action from the geometrical. This terminology, I guess, comes from the geometrical Langlands. I guess the main point of Parks-Schultz work is to actually construct the spectral action here. We don't see a direct way to construct the spectral action on the shifts on ISOC. But since now these two categories are equivalent, we obtain as congruous action. And then, of course, one should say much more about that. But
is equivalence been established by whom?
There's a bunch of people, I can't fully remember.
Is it published?
Not yet. They're writing. Yeah.
Ivanov is one of those guys.
Ivanov, Gleason, a bunch of people like Linus Heim. Yeah. Anyway, it's now it's at least what I heard. It's there. Still, just details need to be written down. Okay, so what's the time now? Let me just finish this main thing and have a break, maybe.
But there's at least an action of this spherical Hecke category on both sides. That should, without maybe not the full spectral action, but at least action is.
Yes, but that's yes. Even now, like this. Yeah. Anyway, most I think because we have now even tame part is already equivalence, certainly it's something. Yeah. So this is, as I said, there's convincing evidence that it's true. So let me, for that, I'll basically state the main theorem and have a break in second part. Assume G is quite split and split over tame ramified tension. Then we can define the tame, the category, the tame part of shifts are isoc. It consisting of those F such that when you restrict to each strata, actually either star restriction or Schrick restriction doesn't matter. When you restrict to each strata, it's a tame representation of the corresponding p-adic group. Or people, I don't know, some people would object to the terminology tame, then we say depth zero representation. It's really meaning it appears as subquotient of the compact induction from some paraholic, and this pi is paraholic acts on pi through the action of the Levy quotient. So that's a so-called depth zero part. For QL bar, you can even define the unipotent representation. Now you just require this pi to be a unipotent representation of T, unipotent representation in the sense of the Nallustig, meaning it appears in the cohomology of finite Nallustig varieties. Okay, so then the theorem is actually the semi-orthogonal decomposition is preserved. If you just restrict to this tame part, you still have this semi-orthogonal decomposition, and the cohomological duality is also preserve this. And similar statement holds for unipotent one, rational coefficient. This actually this is non-trivial, which in fact says the following: if you take 2 points, 2B and B prime, then you can start extension from one strata, JB, and then start restricting a smaller strata. So you get a function from here to here. What's the theorem actually says this function sends depth zero representation to depth zero representation and sends the unipotent representation to unipotent representation, which actually a priori is not obvious, but nevertheless it's true. And I hope there's also actually the whole category has some meaningful depth filtration, such that this function really preserves the whole depth. I mean, okay, so actually you can already ask whether this function preserves depth, because it's depth. It's a well-defined question. I don't know, I couldn't go beyond the depth zero. I don't have such result.
Is that noted the threshold?
I don't think they have. No, they don't.
So it's supposed to be some sort of slope filtration?
No, it's not slope iso. It's just this depth representation category. Yeah, this is just you coming from the Moy Prasad.
But on the other side.
On the other side, it comes from the Galois. How the Langlands parameters should be trivial on certain ramifications.
So it is like the slope.
But it's not considered slope of isoprism.
Do you have a description in general for each factor?
I know you will ask this question.
Oh, I asked it before.
But I'll give you at the end, I'll give you a slide. You will see what is functor. Some example, I don't have a good way to say that, but it's, even in the GO2 case, you will see it relate to level reasoning.
Is one of those not the form of a levy of another?
Huh?
Is one of those not the form of a levy of another?
No, for example, you can take this to be basic division algebra. This is torus. Yeah. You can take this B prime to be basic, which is probably, let's say in a GeO2 equivalent division algebra. And this B, you can take it, so it's like a torus.
Right, but
Yes, I mean, what was it?
it's still composed of passing to an inner form and passing to a labial.
It's
So-
something like that.
so-
They're supposed to be, yes.
So it's a composition of Jacob Langlands and Jacob Langlands.
I don't know precisely whether it is, but sometimes it looks like that. Yes. Sorry, no. It's even more complicated than that. Even more complicated than that. Yes, you will see. All right. So now let's okay. Almost 1 hour. So let me just get to the main theorem and this stuff. So we take the produce objects here. So now once we have all the shift theory and the space, then you can just mimic what the linguistic did, and nowadays people understood in terms of categorical trace or so forth. So it's kind of the now this is kind of standard business or cycle correspondence. So we define the so-called affine linguistic induction. As you take the shifts on the LG modulo pro p Hori, and then take the pullback to LG modulo for Venus conjugation and push forward. But of course, there's an issue is this map now, sorry, this is a pro p Hori. This map now becomes not proper, so you don't do it for arbitrary shifts. You only do those shifts, what I call the monodromic shift. Monodromic shift, but here I really allow arbitrary monodromic. Basically, it's a shifts on the torus direction. It's a tame local system, but then you need to take the incompletion of it. And then for each strata, there's some like a very huge free monodromic objects. It's kind of the induction limit of all kind of various local systems, finite dimensional local systems. But that's like kind of the unit object. For example, when you take W to be E, that's a unit object in this category. This is still monoidal category. And you do this pull back, push forward. A priori, it's this object is huge, but you end up is finite type objects. What do you end up with? Is some object. Actually, these objects are compact objects in this category, although this is not huge. They're compact here. And when you restrict to each B, what you end up with is the cohomology of affine linguistic varieties, or actually covers of affine linguistic varieties. This is so some Y version of it. So these are like some particular. Actually, these objects are from the tame category is basically a category generated by, one can show it's generated by these objects. On the geometric spectral side, we have this stack of tame Langlands parameters, classifying those parameters which are trivial on the Y inertia and one rational coefficient and the group, let's say, unramified, you can have a unipotent part, which requires this a tame inertia acts with unipotent monodromy. So these are really simple. You just write down, because the tame group has basically two generators with one relation. You just write down the general relations. It's just the two elements satisfying this Q commuting relation. If in the unipotent case, you want this element is in the unipotent front. And actually, this is a connected component of the whole thing, really open, closed, connect component. It's not irreducible, there's bunch of irreducible components. This guy itself is a bunch of union of irreducible components in general. Okay, so the main theorem is you do get that is for rational coefficient, you do get the equivalence. coherent shift on this tame stack in the tame part of the local of stack iso tame part of the local Langlands stack. So this again, this somehow follows from this more categorical trace business. But we sort of need to establish some kind of some kind of monodromic version of Kapnikov's equivalence. Once you have that, comes from some kind of standard machinery. Several things.
But does Kapnikov assumes G split?
Oh, but because I assume it's unramified. Meaning when you pass to, because this trace stuff is, when you pass to maximum ramified extension, it becomes split. The Galois extension, the unramified comes from this how you Frobenius acts. Yeah, you can just identify the action of Frobenius on both sides. So you do get like unramified unitary group are in here.
Also, do you have a constructive inversion?
What is constructive?
Without taking compact objects?
I mean, in coefficient or in rational coefficient, that compact and constructive are the same. The integral coefficients are different. But here I'm going to sort of to assume G has connect center here. This has something to do with the current status of the spacecraft tame version of this Romance equivalence. But we expect to remove that verse. Shouldn't be written. But the really thing is something not directly follows from the business is if you take any compact induction from pi, from parabolic, and then you take the compact induction and take the corresponding, that's a representation. You can think about the sheaf. Under this equivalence, actually, this is the really honest coherent sheaf. It's maximum Macaulay coherent sheaf. So, similar statement holds for if you replace tame by unipotent. If in that case, I can even drop the condition G has center. Yes. So maybe one more slides for main results, and then have a short break. And so let's consider the case how this categorical representation is related to the classical local Langlands. Here you have equivalence categories. Classical, you want to classify a representation attached to Langlands parameter. In fact, this is really, as far as I understand, this is complicated, and I don't fully understand the picture yet. But I believe the picture is playing when the representation is discrete series representation. And I couldn't get the discrete series representation yet, but at least I get the supercuspidal ones. So the statement is as follows. Recall that for simplicity, I assume G is semi-simple. No, a parameter is called discrete if the centralizer parameter is finite.
So you assume the parameter is trivial on the SL2 part, SL2C part.
No, it's a-adic coefficients.
Yeah, no. This equivalence is that phi is actually an open point on the stack. It may not be closed. If there's a unipotent monodromy, in general it's just an open point, not closed. And then you can take its closure. This closure actually is the smoothly reducible component of the stack, and in general it's actually really just the affine space modulo sum. It's pro-homogeneous affine space modulo sum reduct. The theorem is if you have a cuspidal reducible depth zero, then the corresponding shift is actually a vector bundle on the closure of this space. So it's not just the supported on the phi itself, because it's a coherent shift, right? The coherent shift can't be just the support on the open. Its support should be closed. So it's really support on closure, and it's a vector bundle on it. In this way, you actually get some enhanced parameter. Namely, you can restrict this vector bundle to this open point, and then this vector bundle becomes a representation of the centralizer group, and that's the parameter appears. All right, so let me just take a maybe 5 minutes break or a minute's break.
Thank you. To be continued soon. Okay. We're back.
All right, so so this is main theory. So let's I have a bunch of slides, talk about some examples, and then have time to switch to the maybe just stop there and talk to informant. Right. So yes, this is supercuspidal. Yeah, maybe I could say a little bit of how this theorem follows actually. People, it somehow follows from really this statement. It's the compact induction. Here I just say one, but in fact for every basic one, it's also true. Not just the G of F or its Turner form. So what happens is the whole point is this supercuspidal, let's say G semi-simple, supercuspidal, or even for simplicity, assume G is simply connected. Supercuspidal are of these forms. So therefore, the supercuspidal will correspond to some coherent shift, maximum Cohen-Macaulay coherent shift. But on the other hand, it's endomorphism. Now it's irreducible representation. Its endomorphism is one-dimensional C. So that means the support of this shift, when you map to the coarse modular space, must be just one point. So then you just see an irreducible component Langlands parameter when its coarse modular has just a constant function on it. There must be a discrete kernel of it must be a closure of discrete parameter. Okay, that's actually otherwise if it's not discrete, you should have some centralizer. You should allow the Frobenius twist on the centralizer of your parameter, so you will get a continuous family of space, and that you will have more functions. So therefore, if your function, if the only constant function, then the parameter is going to be this component should be just just discrete closure of discrete parameter, and from there, then it's when I show if it shifts theoretically supported on some component, then it's actually scheme theoretically supported on it. It's a smooth irreducible component. It's called Macaulay, then it must be a vector bundle. And in fact, you can also show this vector bundle is sort of some irreducible vector. Otherwise, its endomorphism wouldn't be C or something. So the supercuspidal thing really follows from here. It's by this one plus a little bit geometry of the stack. So I expect the same thing holds for discrete series representation, but that's more difficult to do, I think. All right, so let's give some examples of this correspondence. So take G to be quadratic split. So let's say even unramified. I have a hyperspatial K, and the Uahori. They're determined by the pinning. And I use the pro-P Uahori. So then the pinning actually determines the added character of the pro-P Uahori. You take the compact induction, then under this equivalent structure should correspond to it. Actually, there's this compact induction, the whole Uahori, some people whole Uahori, I don't know that. Sorry, not the whole Whittaker. So it's compact induction from UF to GF with character. But some people call it baby Whittaker or whatever. It's like the depth zero part. Actually, the category represent the p-adic groups, break into blocks, and you project the whole Whittaker to the depth zero. It's this one. Yeah. and then its functions, and then under this equivalency correspond to the function structure shift. For example, corollaries and homomorphism. This is just the functions, and yeah.
How do you say statements like that? How do you say statements like this?
Yeah, it's again comes from first we have this like Romance equivalence or some monotropic version. You need to match some objects there, or maybe some module category actually, precisely. One side you have some this Iwahori Whittaker categories. The other side, this coherence on Steinberg acts on Springer, Gorthenich Springer resolutions. You need to match that.
Does this rely on some higher categorical result that is known, or is it
in the Iwahori case it was known, but then probably
Sorry. So does it mean that somehow, if you look at this corollary, does it mean that the right-hand side has no high homology?
it doesn't have no hierarchical homology, yes. In the rational coefficient, it's pretty simple. In the integral coefficient, it's less obvious, but actually, I think Frank-Shelton has a direct proof of this no hierarchical homology. But it's also, actually, we expect this equivalence to be also holds integrally, so this will give another proof.
Which group, the physical? Which
Yes.
equivalence?
Yes, but something equivalent, like a simulation, and the Roman, the already is there's some modular, yes, but then
You're
yes.
gonna lift it.
This yes, but yes, there's no hierarchical homology. And then we have come to this coherence Springer shift, which was I guess I learned the name from David a couple of years ago. So you take the here you have stack of uniform local parameter. You take the Borel version. So it's like so it's basically classifying a stack of L parameter together Borel containing that parameter. Then you push forward the structure shift from upstairs to downstairs, and then under this equivalence, it actually corresponds to the compact induction from the Iwahori to p-adic group. And as corollaries, you get the Iwahori algebra as derived endomorphism. Again, here is no higher homology. Yeah, so for split groups, this was already proved by Dylan and his collaborators.
Do you have a version of this model for tame, all tame parts?
You can do the tame, yes. You take put tame, you take tame to here. But the difference is in the uniform part, the log B map to log G is surjective, but for the tame part, it's not surjective. The map only capture part of it. Because for 10 stack of 10 parameters here, you have like some irreducible representation of irreducible Langlands parameter. Those can't have a reduction to Borel. The difference here, uniform is really surjective. It's surjective. Yeah. And if you take the compact induction of hyperspatial, then you should expect, actually in this case, it corresponds to the structure shift of a stack of unramified parameters. Namely, this is trivial on the whole inertia. In particular, the endomorphism, derived endomorphism, there's no higher derived endomorphism. Right. Let's look at the Steinberg and trivial. This is PGL2. So in this case, the stack of unicorn part, let's just say, actually contain. Actually it's three components. There's this Steinberg component. Actually, Steinberg has the unipotent monodromy, but you can have unipotent monodromy, the unipotent times -1, -1 or something. So actually there are two, and then the unramified component. And it turns out that one can check the coherent Springer shift in this case is just a structure shift on the whole unipotent stack. Direct sum of copy of structure shift on the unramified part. Locally, it looks like if you take the intersection of the two components, it looks like two coordinate line intersection with GMX on one line, let's say X and Y coordinate with weight 2 weights, and on X and has the weight 0. So recall on the there's an exact sequence of smooth representation GF, so it has considered smooth, also local measures on P1. By integration, you have a trivial representation of kernel and co-kernel and Steinberg representation as a sub. Under this equivalence, what actually correspond to is this correspond to actually here I should put plus maybe just one intersection of two components. It's a kind of point on X and Y equals 0. And the whole Steinberg will be basically the structure. The Steinberg representation will correspond to the structure shift on the Steinberg component, namely when X is 0. So you have the when Y is 0, so you have X. And then, but what happens is the trivial representation doesn't really support on the trivial unramified component. It still supports on the Steinberg, full support on the Steinberg component. And but it's not a coherent shift. It's shifted as some cohomological shifts to degree 1, and it has weight -2. So actually, if you move this to the left-hand side, it's the short exact sequence from the ideal shift of this point inside here. The structure shift is the structure shift, and the portion is the ideal shift. So then you just move it to the other. So this is what I said. Really, if you want to consider relation between categorical local Langlands and classical local Langlands, it's complicated. It's not as simple as you think, because like the trivial representation corresponds to something which doesn't support on the unramified component. There's a more complicated thing when you pass to, let's say, syntactic parameters, square root of P, square root of P. So, but anyway, I expect for discrete representations, it's really classic picture and the categorical picture should match. If we consider quaternion, we can also consider the quaternion algebra, it's a different one. So now you take something different, it's classifying, log B, so you consider stack classifying a parameter, and the Borel contains a parameter. Now you just consider something, a parameter together with the Borel, just containing the image of the inertia. So this on the Steinberg component, it's generically it's 1 by 1, it's birational, because on the Steinberg component, you have non-uniform monodromy. So there's essentially only one Borel content. There's only one Borel content in it. On the unramified component, so you have basically have P1 vibration. So yeah, but there's something like a derived structure going on actually. And if you want to see something correct, you need to take care of this derived structure. But let's ignore that. Then we take this element, the antidiagonal 1p, right? So this is a basic element, and its J delta is actually the quaternion algebra. And it turns out that under this categorical equivalence, this compact induction, I mean, this is one from this quaternion algebra, not G itself, corresponds to the coherent structure shift on the Steinberg variety, but twisted Steinberg component, but you put weights to be -1. Okay, I mean, on that component, there's a GM action on X-axis, and then put the weight. It turns out this is actually a self-due cohomology. It's self-due one. Like this, on the Steinberg component, weight -1 is self-due, then weight 0 go to weight -2. And actually, we can even do some integral version, which has something to do with this Taylor-Wiles patch. That's not the. Okay, so now this is the last slide. So talk about this also would help us to understand this functor promise to Janice. So this, we consider more p-fiber of modular curve with no level at p. So it's classifying elliptic curves with some full level at without putting any level at p. There's a famous stratification by you look at the elliptic curve is ordinary or super singular. So it's an open strata, so ordinary strata. It's super singular strata. It's just a bunch of points. And this is open. And then if you just look at the open closed relation, this you get the fiber sequence, the constant shift mapped to the restriction to constant shift to the ordinary and push forward, and then you take the co-fiber, which is shrink push forward back and push shrink upper shrink, I lower star. But then up to here I put cohomological shift, it becomes constant one. Okay, so this is basically here, this one computes the homology of modular curve. This is computed homology of ordinary part. This is like the homology on the super singular part. Basically, it's functions on the quaternion algebras. But it comes from this sequence. The reason I took modular curve is this really have some geometry, but really this sequence happens in the modular local Stukas. It's not you can't draw pictures there. So and then by start push forward, actually it gives a shift sequence of shifts here, and the sequence is actually follows. This middle one actually goes to you have this compact induction from this your Hori to JB, but B now is P1, so it's really just torus. It's like you have this compact induction, take JB, push forward. And here you have this compact induction from the quaternion algebra. The previous appear in the previous slide. Take I lower star push forward. And then there's a co-fiber, some shift I denote by Z. This is so see, actually this is a non-splitting map. This says that the star extension shrink, star restriction get a map to here. But this has some, this is yeah, okay. In this case, I think it's yeah, this case it's kind of probably, yeah, it is parabolic induction and then together with Jackie Langlands.
This is a basic picture with Shigoro varieties that this procedure is involved in understanding how things fit together for KLM.
Yeah. But I mean, right. Anyway, that's you can some sort of understand this map a little, kind of this case. But on the coherent side, it really corresponds to this one. Actually, you push forward some line bundle on the stack for Borels, like ample line. Because the choice for Borel gives you, map some to the P1 and take O1 go back. Here is O minus one. This is the previous one. This the fiber sequence you compute is what happens here is you take the topological two-dimensional vector bundle on the stack of L parameters and restrict to unramified locus. It's a picture. And this map is induced by this inclusion. So you have a upper string, lower star map to it. All right, so I think I stop with slides. Actually, I think I can also just stop this and formulate.
Thank you very much. Questions before we get more informal? Formal questions?
Can you say something about what happens beyond depth zero? Any Any comments?
I mean, I can't say anything definite, but there's some hope.
I mean, is there a conjecture, for example?
Conjecture what? I mean, geometrical Langlands or a classical thing. There's a conjecture. This
No, of course. I mean, like
categorical one. I don't know. I don't have. I don't know any precise.
So
maybe some people in the
can explain what and on the level of conjectures why what is the difference, so to say? What prevents you from formulating conjecture?
Huh? What repeated? Could you repeat the question?
If we're discussing conjectural statements, not proofs, then somehow what prevents you from formulating conjecture? Is it because you don't know what the right-hand side is? Or
you mean the representation? What? Yeah. So the question is consider what is the shift side, right? I mean the coherent side, you certainly can make something.
So I don't understand the question. You made a conjecture. You made a conjecture, and the entire. So
that's arithmetic thing, but
you had your categorical. Obviously, that's independent of depth, right?
Yeah. Okay. So I don't. Yes, maybe I don't understand Shada's question. It's about geometrical Langlands or arithmetic Langlands. Arithmetic Langlands, there is a conjecture, right? For the without any.
Oh, okay. So yes, I forgot about that. Yes. Okay. Fine.
But for geometric Langlands, local Langlands, then yeah, I don't.
No. I meant this conjecture. So if you look in this conjecture, so do you know any? I mean, what do you know beyond depth zero about this conjecture?
You know something, but not systematically, right? So first of all, as I said, the Fox-Schulze has this spectral action which holds for without any restriction on. Let's go beyond the tame situation. Nowadays, there's a sort of like one can try to do some isomorphism of Hecke algebras, which I mean, there's also some, for example, you can also actually get something slightly beyond at least, for example, this gross reader considers this epipelagic, very simple supercuspidal, has some obvious geometric angle, and we can do that. But I don't know, I don't have systematically way to deal so far. But somehow, of course, the idea is now some people believe, some people don't. Is all other blocks is really just the tame block for some smaller group.
Yeah, but if, for example, if you just restrict yourself to cuspidal part, then is it?
Cuspidal part, yes. I mean, there's a bijection of representations.
Yeah, but for cuspidal part, we know that this corresponds to a depth zero situation. But we have an isomorphism.
It's a correspond to the depth zero. Everything reduced
to depth zero.
Yeah. That's but so one hope is, of course, to, I mean, literally. All this, if you look at the stack of error parameter, even just the supercuspidal, of course, in many cases is very simple. It's just point modulo something. But even you look at slightly more complex situation, many blocks are kind of I don't know. For example, if I at least maybe I assume the group has connect center, then all the components are really look like the F0 10 part of some smaller group. So this geometric side, you already see everything can be like the spectral side.
It's especially simple for GLN. So, for example, suppose your group is GLN.
Yes.
How far are you for GLN from proving this conjecture?
First of all, I think David and they're already embedded the full GON smooth representation of GON into the stack of coherent shift on the stack of Langlands parameters. I think with this, I think then the full thing should be within reach, I think. Yeah, GON should be within reach.
But that's still depth zero.
No,
No.
the whole thing, but you just, but you reduce the things that are known, how to reduce everything to depth zero.
Oh, this embedded for John is.
It's for all of them.
Yeah. GON, I think even the full equivalence is shouldn't be really. Yes, but there's a nice, interesting question I propose is actually, I take your conjecture with Finkelberg on this some geometrical Langlands for local geometrical Langlands for GON. So then you can produce some arithmetic situation. So you have some on the stack of parameters. You can consider another space with a chain of representation of smaller dimensions and the inclusion mapped from one to another. Then the conjecture would be that if you push forward the dual line shift upstairs to downstairs, it will, under this categorical local, this arithmetic categorical local Langlands, it should correspond to exactly, compact induction from point to GONF. But I think that kind of statement is not known yet.
Okay.
Yeah.
Any further questions? Let's thank Xinwen again.